Good morning, and thank you for joining us. Today's webinar is on the Fusion, the ideal TOC analyzer for the pharmaceutical industry, presented by Joy Osborne, our TOC product line manager. We will be accepting questions, so please feel free to submit those throughout the presentation, and we will address them at the end. Okay, I'm going to go ahead and hand it over to you, Joy.
Okay, thank you, Shelley. Like Shelley said, today I'll be discussing with you how the Fusion is the ideal TOC analyzer for the pharmaceutical industry. So with that, to help demonstrate how the Fusion is ideal for the pharmaceutical industry, today's agenda will be talking about all the features the Fusion has, pharmaceutical applications and methodologies that are applicable to the Fusion, comparing the different techniques used for TOC analysis and those strengths and weaknesses of each analysis technique and how that applies to the pharmaceutical industry, and lastly, how to best optimize your method for pharmaceutical applications in the Fusion software. Okay, so let's start with the pharmaceutical features of the Fusion. The Fusion has built-in system suitability standards in the software. These are used in USP method 643. It is very easy to set up in the software. Part of this method is running your reagent water to ensure it's under 100 parts per billion of carbon, and then ratioing 500 parts per billion of carbon from sucrose and 500 parts per billion of carbon to 1,4-benzoquinone to make sure they come out similarly, to show that an easy to oxidize compound, which is sucrose, and a difficult to oxidize compound, which is 1,4-benzoquinone, are oxidized at the same rate. More information on this method is in our webinar. We have another webinar that's just on USP 643 and how the Fusion complies to it, and it's on YouTube if you want to check it out later. After the system suitability standards have been run, the software will automatically calculate the ratio of the two compounds, which by USP 643 mandates the compounds need to come out within 15% of each other. The Fusion will give you a quick pass-fail. If the system cannot do this, the system cannot be validated for pharmaceutical applications. As you can see from these results, the Fusion did not have any issues passing USP 643 standards. We also have application notes on our website with more information on the methodologies, sample preparation, and more to achieve this. So you can see right here, you have your reagent water, which has to be less than 100 parts per billion, your sucrose, which is at 500 parts per billion, and your 1,4-benzoquinone, which is at 500 parts per billion, which are ratios, so just divided into each other, times by 100, but the software does this for you and calculates, and it should come out between 85 to 115%. Again, that's proving that the system can handle an easy to oxidize compound, which is sucrose, versus a difficult to oxidize compound, which is 1,4-benzoquinone at the same rate. All right. Teledyne Tekmar also offers an optional IQ, OQ, PQ package, which includes USP 643 testing. So if you don't want to have to do it yourself, we have specialized service technicians that will do it for you. They'll come out to your site. Along with USP 643 testing, they'll do things like a calibration check to make sure your R-squared value, your M value, your B value look good. We'll do a reagent blank check to make sure your blanks look good, that they're clean enough. That's a reflection of the system and your water and your reagents. A cross-contamination challenge, which is a carryover challenge to make sure you're not carrying over too much carbon from sample to sample. An IntelliDilution check, which is also a feature in our software, just verifies that if you have a sample that's above your calibration curve range, let's say you have a calibration curve up to 10 parts per million and you run a sample that's at 20 parts per million, the software will actually automatically flag it dilute it for you, and rerun it. So if you'll still have results in the morning if you're running samples overnight, so you don't have to worry about if all your samples are within the calibration curve, which is really nice. User manager validation, which is just part of 21 CFR 11 compliance, which means there's different levels of users. You're going to have your power user, which is allowed to do everything, edit methods, edit schedules, and then you maybe have a basic user that can only run schedules, and then archive validation to make sure it's properly backing up all your data. Okay. Another feature of the Fusion is, as you can see in the middle of the Fusion, right here, there's 4 125 ml amber bottles that are typically used for stock standards, although of course you can use them for other things like reagent water or things like this. The Fusion will actually take a standard and dilute it at different levels from that stock standard bottle or vial if you like, to build a calibration curve. It can perform up to 1 to 200 dilution, so no dilution 1 to 2, all the way up to 1 to 200. So here's an example of real results from the Fusion where we took a 1 ppm carbon stock standard solution and diluted at various levels and ran it in triplicate using the auto dilution feature. And we did this at the lowest levels we could to test the auto dilution feature and the accuracy and precision at the low end, since it's critical in the pharmaceutical industry to make sure things are as clean as possible. So you really want a good sensitivity. So you can see the results here. So they were tested within 15% of the actual true value. And they all came out within 15%, even including the 0.5 part per billion standard, which is really, really low. In fact, most reagent water has about 50 parts per billion. So there's going to be a little bit of variance there. You can see there's a little bit higher percent RSCs. Again, this was run in triplicate at the lower end, but that's to be expected since it is such a small absorbance count. So when you're averaging out 3 absorbance counts at such a low level, you're going to get higher RSCs. But beyond that, they look really, really good. You can easily expect, less than 5%, as long as you're not, if you're going above like reagent water level, like I said, which is about 50. Okay. And then we do this with all our products here at Teledyne Tekmar. We try to make it as easy on the user as possible, including the location of the glassware. So all the glassware for the Fusion is nicely located on the front. All you have to do is open the door, which is see-through, so you can actually see everything going on in the front of the instrument. So for example, if you are having maintenance problems or you need to troubleshoot, you're going to easily be able to see if anything goes wrong. For example, if the fritz and the IC sparger, this is the IC sparger, so this is where the inorganic carbon is removed, gets discolored, then you probably have contamination. You'll actually see this frit get brown or dirty looking, and then it's time to take it off and clean it, and you just clean it like normal glassware. It's not a big deal, but it's nice because you know right away that there's something going wrong. Same with your halogen scrubber. If the copper side starts to turn brown, then it's time to change out your halogen scrubber. So we also have the 25 ml syringe, which measures the volume of the sample and the dilution volume, that kind of stuff. So it measures the liquid pathway sample volume. We also have a 7-port valve. So this is what moves around the liquid pathway. So it actually turns inside, and where it's turned is where it moves. If you are getting maybe a little leaking around here, some sodium persulfate buildup, you'll be able to see it right away, which is really nice. And then the UV lamp which along with sodium persulfate oxidizes the carbon to CO2, which then is measured by the NDIR. Again, that's something that needs to be cleaned once in a while too if you are doing really low level results. And then if you take off the right side panel of the fusion, you're going to see the rest of the parts, which are also really easy to access for quick maintenance. We have our mass flow controller that's made by our sister company, Teledyne Tekmar. This is a great part because it actually offers features like auto leak checking. So you can just hit a button and the system will leak check it for you. Obviously, if you have a leak in your system, you're not going to get great results. So if you're having high RSDs or low results, that's usually a sign of a leak. So you can easily just click the auto leak check and it will do that for you. It also has a nice feature which is programmable IC sparge flow. So if you have more inorganic carbon in your sample, you can actually increase the IC sparge flow. So you can play around with things like that if you need to, due to this mass flow controller, which is really nice. And then we have our permeation dryer, which removes any remaining moisture that the mist trap did not to prevent any damage to the NDIR detector. And then you have your NDIR detector right here. So again, everything's just really easy to get to. You have some of your valves in here, but it's very basic. All right, and then the fusion is also a tool for 21 CFR 11 compliance. It includes features like electronic signatures, the ability to import and export data to a LIMS type system through CSV. It can auto backup data. So you have that archiving feature, so you don't have to worry about losing any of your data. You have customized permissions for different level of users, which I already talked about. You usually have a power user and maybe a basic user. You have different levels of users. You also have your change justifications. So if you go and change a method or a schedule, you have to put a reason why, and that's for auditing and tracking and things like that. And then on the right side of the screen is an actual excerpt from the software. It shows you how to archive the data. So you just click on System Properties, the Archive tab. You tell it where you want it to go, and then you check the archiving box, and then you can archive it as often as you want, every day, or maybe every 30 days, or whatever you want, and then at what time. And then, so you don't have too much data because you have all this archiving, you can actually delete some of the old archive folders after so many days if you want, which is really nice. That way you're not taking up all your hard drive, that kind of stuff. All right, so let's talk about pharmaceutical applications and methodologies. So the fusion does a lot of different methods. I know I have a lot of environmental methods, and this presentation is about pharmaceutical, but it is also great for drinking water applications like EPA 415.1 to 415.3. But most notably, what we're going to talk about is cleaning validation, USP 643, European Pharmacopoeia 2.244, and Japanese Pharmacopoeia method. All right, so the three major applications we'll be focusing on are clean in place, water for injection, and purified water using the fusion. All right, so these are results from an application note we did. So first of all, I should tell you a little bit about what clean in place is. Clean in place is the method where you swab a surface that comes in contact with drug manufacturing. So TOC is a great method. It's kind of a catch-all method to determine the cleanliness of equipment, since it picks up anything from residual drugs from previous batches, cleaning solutions, bacteria, and foreign objects. Usually all these contain carbon. So if you swab it, you can check for all those things which you do not want in your pharmaceuticals. So these are the results from our application note. So a little bit about the background of the application note: a 1 ppm concentration of the compounds listed, which are very, stereotypical pharmaceutical compounds, were prepared on a stainless steel coupon, which is just like a flat surface, to simulate pharmaceutical equipment, since a lot of it's stainless steel, by spotting 320 microliters of each standard and triplicate onto the coupons and allowing them to air dry. So it's, again, simulating a manufacturing site. And then we swab these coupons with special, clean in place swabs. And then we broke off the tips and we put them in a 40 milliliter vial and filled it with water. As you can see, most of the compounds were recovered above 80%. So here's the recovery rate of each compound, which is extremely good considering the technique is just swabbing it. It's not a direct injection or anything like that. So I thought that was really great. If you want more information about cleaning in place, we have an application note called a cleaning validation swab recovery study using a UV persulfate analyzer, which is our Fusion. It's on our website under the Resource Center tab. And then I chunked water for injection and purified water into one category because they're very similar, because they're really checking low levels of carbon. They're both what's used in the manufacturing of pharmaceuticals. So they're the water used to make it. So it needs to be free of contamination, as low as you possibly can go. So again, using the auto calibration, auto dilution feature, a calibration curve at 10, 20, 10, 40, 50, and 100 ppb. And triplicate was built for my 1 ppm stock standard. The R-squared value was 0.99973, so 3 nines, which is really good, which meets most pharmaceutical standards, which are typically require 3 nines. Because it's, a little more strict than environmental, which is usually 995. But again, it depends on each place. Then check standards with the same values of carbon will run against the calibration curve. So again, I'm sorry, it wasn't exactly the same, but it was similar. A 20, a 25, a 40, a 50, and 100 ppb were run back against the calibration curve. And the accuracy, all of them came out within 10% of each other. Again, these are really, really low levels, so this is just demonstrating the accuracy and sensitivity of the Fusion. Also, the R-squared values were really good, except for, again, when you get really, really low below your reagent level water. Other than that, you can expect, less than 5%, which is really great. All right, so now we'll talk about different TOC techniques comparison. We've talked a lot about UV persulfate, which is the Fusion, but there's also different techniques you can use for the pharmaceutical industry. So the 3 main techniques for TOC analysis are membrane conductivity, chemical oxidation, also called UV persulfate, followed by NDIR detection, like our Fusion, and combustion oxidation, followed by NDIR, like our Lodix and Torch. Of course, with each type of technique, there are pros and cons to each. So let's talk about that. So membrane conductivity has great sensitivity. So you can do real low level parts per billion analysis, which is what's needed for the pharmaceutical industry. It also is great for doing online processing. So if you need to do continuous sampling, like from a stream of water, things like that, like water for injection, it's great for that. It has long-standing calibration, so you don't have to recalibrate very often, which is nice. It's also a well-documented method. The drawbacks with it are that the membranes can clog, so you can actually get particulates and things like that stuck in those membranes, and then it takes a long time to clean out. It can take hours. with a system like the Fusion, it takes, a clean, which takes like 10 or 15 minutes. Amine groups can pass through the membrane, giving false high results, which I'll show you in just a minute. Ionic contamination can cause false low results, which is can be concerning in the pharmaceutical industry, since you think the vessel's clean or the manufacturer equipment is clean when it in fact is not, because it's giving you a false low result of carbon. It has an limited analytical range, so it can usually only do parts per billion to 50 parts per million, roughly. And it cannot handle salts, acids, or particulates. Again, that's because of the conductivity part of it, because things like acids will mess with the conductivity of a sample anyway. All right, so now let's talk about chemical oxidation followed by NDIR detection. It also has great sensitivity. You can get sub parts per billion level. It's easy and quick sample pathway cleaning process. So again, you can clean it up in minutes. If you do run a very dirty sample, it's not the end of the world. You have accurate analytical results, few interferences, unlike membrane conductivity, which I'll show you further, more data to support that a little bit. It's also well documented and established method, and has a large analytical range, usually up to 4,000. Again, that's with dilution. So really, it's not a huge range if you run the sample straight, but we have auto dilution, all that kind of stuff associated with it to get you up to that 4,000 range. So high limitations of it are high level of carbon samples, so greater than 4,000 ppm. So obviously not great for wastewater samples or soil samples, things like that. It's not going to be able to achieve that kind of detection. It's going to saturate your detector. Actually, it's more the oxidation process can't handle oxidizing that much carbon. It cannot run particulates greater than 0.3 millimeters in diameter. So the oxidation of just using sodium persulfate and UV light to oxidize the compound is not strong enough to break up that particulate and oxidize what's in the middle. So you're going to get false low results if you have particulates. It cannot run salt samples of greater than 1%. So salt actually interrupts that oxidation reaction. So if you have more than 1%, you're not going to fully oxidize your sample. You can play around with it a little bit with dilution if you do have more than that. The UV lamps can fade over time, so that can be kind of costly. More sample volume is needed for this analysis. So if you only have very limited amount of sample, maybe less than a 1 milliliter, it's going to be hard to run on a Fusion or other UV persulfate analyzers. And then you can only use really nitrogen carrier gas. The reason I say that is air and oxygen do work. You can run it through it, but with the UV sodium persulfate process, you're going to oxidize your air. So you're going to convert that O2 to O3, so ozone, and then you're going to have ozone venting out into your laboratory, which is not good for your respiratory system, and we want everyone to be safe. You can get around that. There are ozone scrubbers, so some customers have that. But we do still recommend nitrogen just because it's the safest bet, which it can be more costly, of course, than using air, filtered air. And then we have combustion oxidation, which is like our torch and Lodix. The thing with this technique is it's very robust. It can handle a variety of sample matrices, including salt water, particulate-laden samples, oils, things like that. So dirty, nasty wastewater samples. It can handle large amounts of carbon. It usually has a solid matrix options. You can run things like soils or cement powders or things like that to find the TOC. Has a very large analytical range, so usually up to around 30,000, and it's a well-documented method as well. It's not sensitive enough. Typically, it's not sensitive enough for water for injection and purified water. So the detection since there's so much high background carbon coming off that catalyst, so you're using a catalyst and heat and oxygen to convert that carbon to CO2. The catalyst gives off carbon, gives off quite a bit, so it's hard to do really low level analysis. So not the best for pharmaceutical applications. It also can be prone to leaks due to the heating and cooling of the furnace. So, you have all those fittings around the furnace, and as you heat and cool, they expand and contract, and you can develop leaks around it. It's difficult to achieve quantifiable results less than 200 parts per billion. And like we showed earlier, the fusion can easily handle, 10, 20, 50 parts per billion accurately and precisely. And then you have a bit more maintenance because of the catalyst. So you will have to change the catalyst more often, and maybe more other maintenance since you're running dirtier samples through the system. It tends to have more maintenance altogether. All right, so let's talk more about membrane conductivity versus NDIR. I talked about how membrane conductivity is more susceptible to interferences, but I'll show you a little bit more about that in just a second. So here's some normal pharmaceutical compounds that we ran on 2 different techniques. And you can see the recovery on NDIR is slightly better. It's much closer to 100% than membrane conductivity. So you're getting some false low numbers again here. Maybe you think with that false low number, it's an acceptable cleanliness when it's really not. So that's why it's a little concerning in the pharmaceutical industry. You're doing things like clean in place. All right, and now let's talk about salt. So here are different levels of carbon run with salt. So 0.8% sodium chloride. As you can see, NDIR sticks around 100% recovery, while membrane conductivity, you get lower results. You get a false low. And here's with Azide type Azide groups interferences. So we have our control, which is just 2 parts per million carbon using a typical KHP standard. And then we slowly add more and more Azide groups. And as you can see, once you hit 50, you're actually getting a very low negative response. But there is actually 2 parts per million of carbon in that sample. So, once you get to about 5, you're getting about half of what's actually in that sample. And then here's with nitrate groups. So here's your control, both 2 ppm KHPs run. And then you start adding nitrates at 2 ppm, it's still coming out pretty good at about 100%. And then you add 5, you're getting a lower result. By the time you get to 25, you're getting a negative result with membrane conductivity. And 50, it's off the charts. So again, interferences there's a lot of interferences with membrane conductivity. All right, now that I talked about that, let's talk about how to optimize the fusion method for pharmaceutical applications. Okay, so here, the fusion has pre-programmed pharmaceutical methods, including TOC, TC, TC minus IC, and IEC methods. And it also has pre-programmed Japanese pharmacopoeia methods. So here you have a typical pharmaceutical method. It's 9 mils, no dilution, your acid, which removes the inorganic carbon, your reagent, which your sodium persulfate, which helps oxidize the carbon. You want to rinse the UV reactor, so that would help with carryover, how many times you want to do it. IC sparge time, so you want to increase that if you think you have a lot of inorganic carbon in your sample. Pre-sparge time is the amount of time the sample is left in the UV chamber with the sodium persulfate. So it's just sitting in there with the UV light before it starts sparging. So if you have a little bit high, if if you have higher levels of carbon or harder to oxidize compounds, you want to increase that number. Okay, so let's talk about optimizing it for less than 1 per ppm. So if you want to go even lower, here are some things that I recommend doing. So if you're trying to do really low level purified water, water for injection type applications, you can take that default TOC pharmaceutical method and increase the sample volume. So it was 9 mils, now it's 10 mils. You can lower the acid and sodium persulfate volume. Since there isn't as much carbon in the sample, it doesn't need as much of these. And because due to the nature that, most things, well, pretty much everything contains artifact carbon, you will get some contamination or residual carbon from your phosphoric acid solution, and more notably from your sodium persulfate. There's always a little bit of carbon in sodium persulfate. So if you lower that, you get less artifact carbon coming from those. In fact, there has been some research to show that actually when you hit levels of less than 1 ppm carbon, you don't even need sodium persulfate. You can actually take this down to 0 because the UV light is enough at that point to oxidize the sample. So something to consider if you're doing really low level. Also, I recommend if you're doing really low level analysis, to turn the UV reactor pre-rinse on. You just want the system as clean as possible with very little carryover. So you're going to turn that on, and then you want to set it to a volume that's equal or greater to your sample volume. So it goes up the walls of the UV reactor at the same height that your sample is, so it's washing down those walls real good for you. You can do it multiple times if you want, if you really want to clean it out between samples. But just so you know, there's a trade-off with that, because the more times you rinse it, the longer your sample analysis time. So I just kept it at 1. And then I also increased the pre-sparge time just a little bit. It's probably not necessary. The only reason I did that was because I lowered the sodium persulfate. But like I said, it probably doesn't need that because at less than 1 ppm, there's enough UV light. So if you did take this down to 0, I would increase this parameter, the pre-sparge time. So again, that's the time the sample and sodium persulfate sit in the UV chamber, UV reactor, and it gives it time to oxidize, and then it starts sparging, which sweeps it to your NDIR detector. All right, so in conclusion, the Fusion has great software features like 21 CFR 11 compliance, system suitability, and auto calibration. It easily performs low-level analysis needed for purified water and water for injection. And it's the superior TOC technique for sensitivity and accuracy. We showed you, again, how easy it can do parts per billion analysis. And then on the accuracy side, how robust it is to interferences versus other techniques. So in conclusion, the Fusion is the ideal TOC analyzer for the pharmaceutical industry. So with that said, it's time for questions.